Okay, so it's my pleasure to introduce Trevor Wilson from Miami University in Ohio, and he will speak on logical and topological characterizations of supercompact and huge cardinals. You're on, Trevor.
Thank you. I'd like to thank the organizers for inviting me and for allowing me to speak remotely, and I'm sorry that I couldn't be there in person this week. Yeah, I want to talk about a few new characterizations of, supercompact and huge cardinals, but in fact, more generally, anything that can be characterized in terms of normal fine ultrafilters, it will turn out. And by the way, please feel free to interrupt at any time with questions or comments. I've only got 20 slides here. Some of them are fairly dense, but I don't anticipate any problem getting through them in the allotted time. So please feel free to jump in at any moment. So first, let me just give some background on fine measures and strongly compact cardinals, which were first to be studied and are known to have a variety of equivalent formulations and applications to other areas of math outside set theory. So the basic definition is if you have a set A, and this is a bit more general than strongly compact. If you have a set A and a S, just any collection of subsets of A, so we're typically going to consider like P kappa of A, a collection of small subsets, but an ultrafilter on S is called fine if for every element of A, there's U almost every set in S containing it. So in other words, the ultrafilter contains the cones over every over every element X of A. And then, of course, U is called kappa complete if the intersection of fewer than kappa many large sets is large. And then, as I mentioned, for strongly compact and supercompact, we consider the set S to be P kappa of A, so that the collection of all small subsets of A, the subsets of A of size less than kappa. And so then we can define, and this is just one of the many equivalent definitions of strongly compact, kappa is strongly compact if for every set A, which may as well just be a cardinal lambda, but I prefer to talk about just to use the notation of a set A. For every set A, there's a kappa complete fine measure on P kappa of A. And so this is, as I mentioned, a large cardinal notion that has a lot of equivalent characterizations. So some of them may be appearing more natural, such as the ability to extend kappa complete filters to kappa complete ultrafilters, but this definition in terms of fineness is just the one that will be most useful in this talk. And so this relates, as I mentioned, it's known to relate to many other areas of math, such as topology. And so let me give a bit of background on box product and topology and the topological notion of compactness. So if you consider a family of topological spaces just indexed by an arbitrary set AI are the topological spaces, and then for every infinite cardinal, the less than kappa box topology on the product of these spaces is generated by basic open sets of the following form. So they're just generalized rectangles, basically, which consist of open sets in each coordinate, and kappa is involved in the sense that we require, almost all of them to be the entire space. So in other words, the ith set is not equal to the whole ith space for fewer than kappa values of I. And so this may seem familiar because in the case kappa equals omega, well, the less than omega box topology is just the product topology, where you've only got, in a basic open set, it's only got something going on in finitely many of the coordinates. And so a generalization of the notion of compactness, the topological space is kappa compact if every open cover of the space has a subcover of size less than kappa. And so open cover just means a family of open sets covering the space. So whose union is the whole space, and has a subcover of size less than kappa, means just a subfamily of fewer than kappa, many of the sets in the open cover, whose union again is the entire space. And it's important to note here that the open cover can have any size. You can cover it by any number of open sets, and then always find a subcover of size less than kappa. And so again, in the case kappa equals omega, well, omega compact is just the usual topological notion of compact. Every open cover has a finite subcover. So basically what we're doing here is we're generalizing the product topology and the normal notion of compactness to the less than kappa box topology and the notion of kappa compactness, or sometimes called less than kappa compactness. There's I'm not sure actually which notation is more common, but anyway, the idea is reflecting things to size less than kappa, getting an open cover of size less than kappa. And so in terms of these notions, there's a fairly well-known topological characterization of strongly compact cardinals, which, as far as I know, is folklore. The following statements are equivalent. First, kappa is strongly compact. Second, the topological notion of kappa compactness is productive. So under less than kappa box products. So any less than kappa box product of kappa compact spaces, it's itself kappa compact. So this is a generalization, or it's a version of Tikhonov's theorem on the fact that if you have spaces that are compact in the usual sense, and you take the product of them in the usual sense, then it's compact. And that corresponds to the fact that omega counts as a strongly compact cardinal, unless you specifically exclude it from the definition. And so this is just a version of that higher up at an uncountable strongly compact cardinal kappa. And so then, okay, there are various weakenings of 2. So special cases that still imply strong compactness. So 3, you could say any less than kappa box product of discrete spaces, as long as they each have size less than kappa, is kappa compact. And in fact, it's sufficient just to consider 2-point discrete spaces. And so in fact, I mean, this is stated in topological terms, but the topological spaces here are not terribly interesting from a topological standpoint. So they just come from discrete spaces by taking products. So the topology here, the only topology actually comes from the definition of the kappa box product. And okay, note that 2 implies 3 just because every discrete space of size less than kappa is kappa compact. Kind of trivially, you can just get a subcover by just picking something that covers each point. And okay, so what we're going to do to first, so the title was Topological and Logical Characterizations of Supercompact and Huge Cardinals. So first I want to talk about topological characterizations of supercompact cardinals. So supercompact, I'll go over the definition, is stronger than strongly compact. So we need to strengthen one of these conditions here. And so what we'll do is we'll modify condition 3 here to strengthen it by weakening the hypothesis. So we weaken the hypothesis that you've got discrete spaces of size less than kappa to actually allow very large discrete spaces. But then if you do that, you will need to weaken the conclusion of kappa compact, right? Because if you have a discrete space that's too large, greater than or equal to kappa, then it's already not kappa compact itself. So you certainly could not require products of them to be kappa compact. However, we can still say something in terms of, in some sense, subcovers of open covers. So the idea is that strong compactness can be phrased in terms of open covers having small subcovers. Super compactness can be phrased in a similar way if we just tweak things a little bit. And so what we're going to do, so the question is, can we find a topological characterization of super compactness in terms of open covers of something, some space, some product of discrete spaces, in fact, having subcovers in some sense which we have to weaken a little bit of size less than kappa. Okay, first of all, I should define supercompactness. So let A be a set. Again, it's often just a cardinal lambda, but instead of talking about a cardinal lambda, I'd like to talk about a set A in this talk. So let A be a set, and let S be a collection of non-empty subsets of A, and then let U be an ultrafilter on that. And it's called normal if every regressive function on S is constant on a large set, on a set in the ultrafilter. And here regressive means just that F of any set B in the domain is an element of B. So in the kind of simpler case of instead of being defined on various subsets B, if F is just defined on ordinals, then this would say F of something is less than that thing, and so that's why it's called regressive. But actually, so a regressive function is just a choice function, or you can even write it concisely as F is in the product of the sets S. I'm actually not sure why I wrote that. I'm not going to use this notation, but that's a way to describe it. And so kappa is super compact if for every set A, there is a kappa complete normal fine measure. So that's the new part is normality. I mean, that's what's not present in the definition of strong compactness. And fine measure on, I wanted to remove the empty set just because in the definition of regressive, F cannot of course choose an element of the empty set. But the empty set doesn't really matter here. So, okay, we need to do something now with normality in a topological setting. And so what are we going to do? And why are we going to do it? In set theory, normality is a natural property that comes up a lot, and supercompactness plays a central role in set theory, whereas strong compactness is kind of the odd one out in the sense that it doesn't neatly fit. It's not known how it fits exactly into the large cardinal hierarchy with identity crises and so forth, and the question of its consistency strength. But on the other hand, in other fields like topology, normality doesn't come up much, and strong compactness is often good enough, and so strong compactness comes up more often. But we can actually get a connection between topology and supercompactness. Namely, the following statements are equivalent for every infinite cardinal kappa. First, kappa is supercompact. Second, looking again at products of discrete spaces. So for every discrete space I, actually powers of discrete spaces is all we need to consider. For every discrete space A, every set I, which might as well just be a cardinal again, and every open cover, so by open sets OX of AI, note that A is the index set of the cover, and AI, this I-fold product of A is the set being covered. So for every open cover of this, open in the less than kappa box topology, there is a subfamily, so indexed by some set B of size less than kappa, which covers not the whole space, but it covers BI. So as I mentioned, we have to weaken the notion of open cover, of subcover here. And so we're weakening it in a kind of diagonal sense. So a subfamily given by a small set B covers not the whole space AI, but the subspace B to the I. Okay, so why does this make sense? How is it related to other things? Well, note that strong compactness is already enough to get, if you start with one set B1, which is a small subset of your arbitrary set A, then you can get, using strong compactness, a subfamily indexed by a different set B2 of size less than kappa, but possibly larger than B1, which covers B1 to the I. However, supercompactness is what's needed to kind of catch your tail in this process and get B2 to be equal to B1. As in this definition here, just both called B, you could consider this as a kind of diagonal subcover, a weakening of subcover, diagonal subcover, just in the sense that B appears twice. And I don't know, I guess that's called diagonal because in the definition of diagonal line, it's a set of all points x comma x, so x appears twice. And so, anyway, this is the first topological characterization of supercompactness that we are going to obtain. And I should mention, so it's convenient to state this in topological terms. I don't claim that this is the kind of property that's interesting to topologists per se, especially because it doesn't involve the usual notion of subcover. However, it is nice and simple, and so I think it's good to look for various new simple characterizations of large cardinals. Okay, so how are we gonna? I want to mention before talking about the proof, there are various characterizations along these lines. And so you might maybe not like the less than kappa box topology. You might like the product topology better. So that's generated by smaller boxes, right? Finite ones. If you want to do that, though, if you're not talking about the less than kappa box topology, you have to involve the cardinal kappa in some other way, right? In order to characterize kappa being supercompact specifically. And so, namely, we can do this in the index set of the open cover. So here, this one maybe looks a little bit more technical, but kappa is supercompact if and only if for every discrete space A and every set I and every open cover. Now, by open sets O sigma, now the sigmas are indexed not by elements of A, but by small subsets of A. But it's an open cover just in the ordinary product topology. Then again, there is a small b, a b giving a small subcover. So there's a b less than a of size less than kappa, such that if you look at just the open sets indexed by p kappa of b, then it covers b to the I. So you've got a subcover, but covering something smaller. And again, the thing being covered is, it corresponds to the thing doing the covering. So a kind of diagonal subcover in a sense again. And one thing to note about this is that we can actually tweak it a little bit more. So if we define for each B, the open set OB to be the union of O sigma for all sigma and P kappa B, then we get an open cover that has the nice property that it's increasing. So meaning if you increase the index, which is now a set, right? B is in P kappa A. If you increase the index, then it increases the open set. So that's what I mean by increasing open cover. And then if you do that, the nice thing is that the conclusion of 2 here, instead of saying that this subfamily covers BI, you can just say that just a single set OB covers BI. So in other words, BI is just included in the open set OB. And so that observation leads to the variant, which is actually a bit simpler to state, which I state on the next slide. So here's another related characterization, topological characterization of supercompactness. So kappa is supercompact if and only if for every discrete space A and every I again, and every now increasing open cover of AI, increasing indexed by sets B and P kappa A, then there's a single B and P kappa A such that the corresponding subspace BI is contained in the single open set OB. And then okay, I'm giving lots of variants of this. The point is not to that I expect people to get familiar with all of them, but the point is, well, first, just that it's a fairly robust characterization, so there are a lot of ways to tweak it and it still works. And then the other one is I want to get to one that's especially easy to prove, and because then I can actually outline the proof in the talk, because it's not actually that difficult. And so the one that I'll sketch a proof of is the following dual form of this. So you look at closed sets instead of open sets. So you just, instead of the open sets OB, you look at their complements. I'll call them gamma B. Those are closed sets, of course. And then we take the contrapositive of this condition above, and then we get the following dual form. This is kind of like, so in the ordinary notion of compactness, you have covers by open sets having finite subcovers, and then the dual version has to do with if you have a collection of closed sets with the finite intersection property, then the intersection of all of them is non-empty. And so this is kind of a version of that that has been tweaked to involve, to give normality, to give supercompactness of kappa. So kappa is supercompact if and only if for every discrete space A and every I, and every, in this case for the closed sets, they're decreasing family of closed subsets, gamma B, meaning that as B gets larger, gamma B gets smaller. We require the closed sets to be non-empty, but actually more strongly, if for each B, the closed set gamma B has non-empty intersection with B to the I, then the intersection of all the closed sets is non-empty. So again, this is kind of like a dual form of compactness that is defined in terms of a kind of a intersection property for closed sets. And so this is the form that will be convenient to prove, and so I can actually sketch a proof of both directions. So the first one, so 1 implies 2 is going to be fairly straightforward, which is not surprising because supercompactness is just powerful and convenient to use. So if something is a consequence of supercompactness, then it should be so by a simple proof, and it is. And then, but the reverse direction 2 implies 1 is also fairly simple, so I can pretty much outline the whole proof. It's simple, but as far as I know, it is new, and the main idea I think is new. Okay, so how do we outline this? So the proof of 1 implies 2, starting with supercompactness, is, as I mentioned, fairly standard. So let A be any set understood as a discrete space, and let I be any set. It could just be a cardinal. That we're just taking the product of I copies of A, right, to get the product space A to the I. And then by supercompactness, we can let U be a normal fine ultrafilter on P kappa of A. And then let gamma B be a decreasing family of closed subsets of A to the I, as in statement 2. And then suppose the hypothesis was that for every B, the Bth closed set intersects Bi, has a non-empty intersection with Bi. And so you can then choose something in that intersection, xb, or I'm writing x vector b because it's so it's an I tuple of elements of B, right? Ordered I tuple. I of course could be very infinite and very large though. But so you have this infinite I tuple xb in the Bth closed set and also in Bi. And this is the kind of thing that you can apply normality to, right? So it's in Bi, so the ith coordinate is in B, and so mapping B to xbi is a regressive function. Maybe I should have said that explicitly. So mapping B to xbi is a regressive function. So by normality, it takes some fixed value, say xi, on a measure 1 set. So looking at the sequence, this I sequence of fixed values, we get a single x. And then we claim that that single x is in the intersection of all the closed sets gamma B, which is what we wanted to show, that the intersection of all the closed sets is non-empty. Okay, if not, then it fails to be in one of them. So it's in the complement of some gamma B. The complement is open. So by definition of open sets in the product topology, this fact is guaranteed by just finitely many of the coordinates. And then you look at, I'm kind of going through this fast because, as I mentioned, it's like a standard application of normal fine ultrafilters. And so what you do is you now take, we had these finitely many coordinates corresponding to finitely many measure 1 sets. Take the intersection of the corresponding measure 1 sets, take something in the intersection which is also in the cone over B, so containing B. So we can do this. So this is where we use fineness. We already used normality to fix the value on a measure one set. And now we're using fineness. And now we get a contradiction just because, so if you just look at the various things that were already said, this xb prime is in the b prime closed set, which is by this decreasing property contained in the bth closed set. And xb prime agrees with x on these finitely many coordinates of interest. But x itself is not in gamma b, so we get a contradiction. So the main point here is this is a fairly standard application of normal fine ultrafilters. However, it does seem to use normality and fineness in essential ways. So it makes sense that you might be able to reverse it to get an equivalent property to supercompactness. And in fact, that's what we can do. So that's the other direction 2 implies 1, which I will outline next. This is the key technical step in the argument, which as far as I know, is a new idea, although not a very complicated one. And so, again, let A be any set, and to show supercompactness of kappa, we want a normal fine ultrafilter on p kappa of A. And so what we're going to do, this slide is kind of dense. Maybe I won't try to go through everything here, but I should say, like, what space AI do we consider? So how big a product of A with itself do we have to consider? Well, enough to enumerate all regressive functions on p kappa A, because those are what we have to deal with to ensure normality, right? We have to consider all the regressive functions on p kappa A and ensure that each one is constant on a measure one set. So let Fi be all the regressive functions, and then we can define a decreasing family of closed subsets of AI as follows. And we're going to use this notation B hat for the cone in p kappa A over a set B, just all the things in p kappa A containing the given set B. And so in our decreasing family, the Bth closed set gamma B is going to be the set of all I tuples in the product, such that the following family of subsets of p kappa A has the finite intersection property, meaning the intersection of any finitely many sets in this family is non-empty. And so because we're going to want these sets to be in our ultrafilter, so of course then that means the intersection of any finitely many of them has to be non-empty. And so which sets should have the finite intersection property? Well, the pre-images of all the xi's. The xi's are like guesses of what the constant value of the ith regressive function should be on a measure one set. And then also have finite intersection property with this cone included as well, because if you can include all cones and still have the finite intersection property, then that's fineness. That's how we're going to get a fine ultrafilter. And so note that that the Bth closed set intersects Bi, because what does it contain? We have to show that it contains something. It contains xb, where in the ith coordinate, its value is obtained by applying the ith regressive function to B itself. And so if you do that, then why does that work? It's because this entire family has non-empty intersection. So actually not just a finite intersection property, its entire intersection is non-empty just because it contains B itself. And if you think about what's going on here, it's basically that if we only require fineness with respect to a single B, then it's easy to get a normal ultrafilter that's fine with respect to a single B, because you can just look at the principal ultrafilter generated by the element B. And so that's all that we're doing here. But the reason I mentioned a finite intersection property is we want gamma B to be a closed set. So to ensure closeness, we have to talk only about finite things. So we're talking about finite intersection property of this family. And then by the statement 2, which we were trying to show was equivalent to supercompactness, the intersection of all these gamma b's that we defined, the intersection of all of them must be non-empty. So we can pick some I tuple x in the sequence of all of them. And then that basically codes enough information to define the desired normal fine ultrafilter, because for that x, that means that it basically chooses good values for the regressive functions. So the preimage under the ith regressive function of this value xi, if you look at all of those, and you look at all of the cones now, because this is in all of the gamma b's, if you look at all of the cones, then this has the finite intersection property. So if you have a set with the finite intersection property, then you can extend it to an ultrafilter. In fact, it already is an ultrafilter. You can show that, so you don't even need to extend it, but you certainly can see that it extends to an ultrafilter. Clearly, it's normal. Why? Just because we included all of these sets in it, the preimages of the xi, so that ensures normality. It's also fine because we included all these cones in it. That ensures fineness. And what about kappa completeness? Well, just being normal and containing all the cones over elements of p kappa a actually implies kappa completeness. And so then this gives the desired normal fine ultrafilter witnessing supercompactness. And so then, so we can generalize this to other large cardinals, in particular huge, I wanted to say something about. So recall, this was our main result here. I'm just stating it again for reference. And then our proof of this, which we outlined, actually is not unique to supercompactness in particular, but you can see it was just a general thing about normal fine ultrafilters. So it actually gives the following very general lemma, that for every set A and just every collection S contained in PA, so S could be P kappa of A, that's what we considered before, but it can just be any sub-collection of the power set. And then the existence of a normal fine kappa complete measure concentrating on that S is equivalent to the statement that for every I and open cover of the product space AI in the box topology, less than kappa box topology, then there's some set in S. So before that was a small set, right, in P kappa A, but in general there's some set in S such that the corresponding subfamily of the open cover covers the corresponding subspace BI of the space AI. So we just consider the S equals P kappa A case before, but it's really very general. Okay, so what about huge now? Huge cardinals. So supercompactness uses, as I said, normal fine measures on P kappa A. If we replace P kappa A, which is also called A to the less than kappa, by A to the kappa, meaning the collection of all subsets of cardinality equal to kappa, then we get huge cardinals, right? And so there are equivalent definitions. So the one involving normal fine ultrafilters is the relevant one. Kappa is huge with target lambda, some cardinal greater than kappa. If for some or equivalently every set A with cardinality lambda, you could just take A equals lambda, but I just wanted to call it A. There is a normal fine kappa complete measure on the set A to the kappa. And then huge just means huge with some target lambda above kappa. And then this is often defined via elementary embeddings, just like supercompactness can be, right? Although I didn't say that, but I'll say it for huge. Huge with target lambda means there exists an elementary embedding like this. And in particular, I'll just say hugeness, it's equivalent to the existence of an elementary embedding with critical point kappa and such that the codomain is closed under J of kappa sequences. So it has a fairly natural definition in terms of elementary embeddings and equivalently in terms of normal fine measures, and we're going to use the normal fine measure version of it. And so what can we say about that in terms of this topological stuff? We can say that the following are equivalent for all infinite cardinals. So kappa is huge with target lambda if and only if for some or equivalently every set A of cardinality lambda, again, you could just take A equal to lambda. And then for every set I whatsoever, which again could be enormous, and every open cover of the set A to the I in the less than kappa box topology, the difference is now we have a subset of A of cardinality exactly kappa, such that the corresponding subfamily covers the corresponding subspace. And so the details here maybe aren't so as important just as the fact that we're characterizing hugeness by a reflection property. So it's just saying that for everything of size lambda, and everything about that, every open cover of this AI could be much larger than lambda, but anyway, it's something about lambda and it reflects to something of size kappa. And so the nice thing about phrasing it as a reflection property is that this characterization makes it very simple to see certain things, like the fact that, I mean, this is not hard to prove otherwise, but it makes it even easier to see that if kappa 0 is huge with target kappa 1, and kappa 1 is huge with target kappa 2, then you can put them together. Kappa 0 is huge with target kappa 2. So to see that using this, you start with a big set A2 of size kappa 2, indexing some open cover of A2 to the I. And then you reflect it down to something of size kappa 1 that kind of covers itself in this sense. And then you again reflect it down to something of size kappa 0, which covers itself in this sense. So if you have reflection properties from kappa 2 down to kappa 1 down to kappa 0, then clearly you can chain them together. And so that gives, I think, a convenient way of thinking about things like hugeness. And sorry, I accidentally went to the next slide too soon. But okay, yeah, let's go to the next slide. Now, I talked about open covers just because that was the way I motivated it. I said that strong compactness has a definition in terms of open covers. And but we don't have to talk about open covers. We can talk about, it's also natural, I think, to talk about total open relations from the product space AI to A, meaning, so we have a relation subset of AI cross A is called total if for everything in the domain, that's A to the I, then there's a thing in the range corresponding to it. So if there was a unique thing in the range, then we'd call it a total function, but there could be more than one Y here, and so it's a total relation. And so what we showed just in this terminology is that kappa is super compact if and only if for every A and I and A to the I, and if you have any total relation from A, sorry, this should be A to the I cross A. So a total open relation from A to the I to A in the box topology, then that totality reflects down to a small set. So there's a B of size less than kappa such that the relation intersect B to the I cross B is total on B to the I. So just totality of relations reflecting down to something small. Totality of open relations in the less than kappa box topology reflecting down to something small. And you get a similar characterization of hugeness in terms of for every total open relation on now something of size lambda, and that should be from A to the I to A. Then there's a set now that we're reflecting to a size exactly kappa, such that totality of the relation reflects to that set. So actually, if you're not interested in topology per se, then this is maybe even more natural. You just have total, consider, what does it take to reflect the totality of a relation infinitary, right? The important thing is I could be really huge, because otherwise it's actually easy to reflect with the Lebenheim-Skolem argument, but this could be really huge. But if it's an open relation, then its totality reflects downward. That's equivalent to these various large cardinal properties. And so this is another way to phrase it. And you could think about so total relations are nice, but what about total functions? Those are nicer. So we could think about those. So what about just the notion of reflecting closure under continuous infinitary, well, I said functions, but I'll say operations, because so instead of an open set such that for every x there's just some y with x, y, and r, you could talk about uniqueness. So you could talk about, let's call it f now, such that for every x there's a unique y such that x, y is in f. So that's the definition of a function. And then since a is discrete, for the function to be open, it's a weird thing to talk about, right? An open function, but it in this case it's just the same as a continuous function. Well, it's actually the same as being clopen, which is the same as a function being continuous. And also, what does it mean for a function to restrict to something total on B? It just means that B is closed under the function, right? So now we're talking about closure under continuous functions, which is even more natural. Unfortunately, depending how you look at it, for me, I thought it was unfortunate. This version where you replace, where you require uniqueness, so you're talking about functions, this version has no large cardinal strength. So kappa, even if it's not super compact or huge or anything, just any infinite cardinal with kappa less than kappa equal kappa. And so then if for all sets A and I and every continuous kind of I-ary operation in the box topology, then there's a subset of size kappa, so it's kind of small subset that's closed under F. So getting things closed under continuous functions is very weak, and the proof uses the delta system lemma. So this shows that the lack of uniqueness of the y here and what we were considering is crucial. Whether that's fortunate or unfortunate, I don't know. So anyway, you can't have a version involving continuous functions instead of open relations. Now I want to say just a little bit in terms of infinitary logic here, because all the stuff about topology and about open relations might seem a bit ad hoc, although it's not complicated, but it's ad hoc. And so what's really going on here is that the statement that we're reflecting downward, the statement about totality of this open relation that we're reflecting downward, you can write it in a more logical form as saying that the structure, as a certain structure on A, satisfies this sense of infinitary logic, infinitary meaning infinitary quantification and infinitary disjunction, so L infinity infinity. And so here what are the atomic formulas? The R alphas are atomic formulas corresponding to the basic open sets in the box topology, whose union is our open set R. And what's the structure here? It's kind of a yes. I will speed up a bit. The structure here is just equipped with all the less than kappa ary relations on the set. So you can actually refer to all of them. The vocabulary is very large. And what can we notice about this thing that we're reflecting? It doesn't involve any conjunctions, just infinitary quantifiers and infinitary disjunctions. And so, in fact, maybe in a sense, that's really what's going on here. So the logical characterization is that kappa is super compact if for every structure and every infinitary but first order sentence with this limitation on its arity and this limitation on its conjunctions, then it reflects downward from A to some small substructure of size less than kappa. And again, the version for huge is that you reflect the same thing, but you reflect to a substructure of size exactly kappa. And so this is kind of, these are like Levenheim-Skolem-Tarski properties now for a certain fragment of infinitary first order logic. And one thing that's a little weird about this is so the arities are kind of big. But recall in the topological characterization, we could replace the box topology with the product topology. Here we can replace infinitary relation symbols with finitary relation symbols, but then how is it going to be tied to kappa? You have to do it some other way. And so that's what the next version says. It just says that you can use finitary relation symbols if you allow some conjunctions, but only the ones of length less than kappa. And so this is, I won't read the whole thing, but it's a fragment of infinitary first order logic for which a Levenheim-Skolem-Tarski reflection property is equivalent to supercompactness. And the corresponding reflection property to things of size exactly kappa is equivalent to hugeness. And a caveat here, so there's no limitation on the size of the vocabulary. So the structure A can include all finitary relations on A, and the sentence C can refer to all of them. And I should just mention a few related results. Sorry, I should have left more time for this part. So this is maybe reminiscent of the Magador characterized the least supercompact as Levenheim-Skolem-Tarski cardinal for L2 finitary second order logic and finite vocabularies, and this is really more natural, right? So I mean, this Magador's result is, I think, much more fundamental than what we're doing here. However, that approach does not generalize to huge, because if you look at what huge cardinals do to reflect L2 second order sentences, it's too weak. The reflection property itself reflects. So you need infinitary logic to, I think, to characterize huge cardinals. Or something related is that Will Boney, based on a result of Benda, characterized huge cardinals via compactness for type omission, and that maybe is somehow reminiscent and maybe even related to what we're doing here, but I didn't really figure out what the relation might be. But that would be worth looking into. Just superficially, I seem to be doing a different thing than Will Boney was doing, but I don't know, maybe there's some hidden relation there. And so the proof of the logical characterization, since I'm just about out of time, I won't read through it, but the forward direction is quite routine. Just a standard application of if you have a normal fine kappa complete ultrafilter, how can you use that to reflect logical sentences? Well, you just use a version of Wasch's theorem. You just observe that the thing we're trying to reflect is basically something that can be taken care of by the usual argument for Wasch's theorem. And so that's all the forward direction is. And then the reverse direction is just, as I said, you look at the topological characterization I gave, and you just look at the logical form of that statement about open covers, or equivalently about reflecting totality of open relations. Okay, so I should stop here. Thank you.
Thank you. Thank you very much. It was very nice. Questions or comments? Yes, Matteo. The question was why discrete and not compact in the topological characterization?
Well, it might be possible to say something about compact, although perhaps more complicated, or maybe it's not possible. I didn't think about it too much, so that's definitely worth thinking about. But I mean, one thing that might make it difficult is, okay, let me find that topological characterization. Okay, so first you are probably thinking about, for strongly compact, this is the nice characterization, right, is number 2. Whoops. So can we get something like that? So the thing is, I think that this supercompactness version is kind of a diagonal version. So the thing doing the covering corresponds to the thing being covered. And the correspondence is the thing indexing the subcover is B, and the thing being covered is B to the I. And so B is just a subspace of the discrete space A. And B over on the left-hand side here, it's just a subset of the index set. So the index set should probably not be thought of as having any topological structure. So A and B as index sets here don't have any topological structure, and so they should probably be considered as discrete over here. And so if you want to, instead of a discrete space A, have a I-indexed family of just arbitrary kappa compact spaces, then to me it's not even clear what the statement should be, although there may well be some version that I just didn't notice, so it's worth looking into.
Thank you. Thank you. Other questions? Yes, up here. The question was, tell me if I get this right. Can you generalize your topological characterization of huge cardinals to characterizations of I2 cardinals by taking some kind of product structure of the ultrafilters? Is that approximately what you asked? A direct limit. Sorry, a direct limit of these.
I did not really think about that. And one could also try to characterize almost huge, I think, in terms of direct limits. And I didn't think about that either. And I think those are worth thinking about, but would be not entirely straightforward. So I didn't figure it out. I will mention though, one generalization that is straightforward is from huge to n huge. I would have mentioned that if I had more time, but that one is just because n huge can be easily defined in terms of a single normal fine ultrafilter.
Okay, more comments? Yes? Huge with he's saying measurable cardinals give a characterization, can be characterized as huge with what kind of sets? Yes. If only if it's huge with charge. Okay. A measurable cardinal is a cardinal is measurable if only if it's huge with target kappa. And so he's wondering whether you can restrict the characterization of huge cardinals to get an alternate characterization of measurable cardinals.
You can get an alternate characterization of measurable cardinals, but I thought, at least the way I was thinking about it, is that measurable is a fragment of supercompactness, and so in the one for supercompactness, then I didn't mention it, but there's a local version. You can say kappa is lambda supercompact if this holds for every discrete space of size lambda. I can still be really big though, bigger than lambda. And then measurable is the same as kappa supercompact. And so then if you require A here to have size kappa, but again, I can be very large, then you get a characterization of measurability.
Okay, that was good. That was the question you sent. Others? Okay, let's thank Trevor again.